Good afternoon, everybody. We've just finished talking about the anatomy of the heart, and today we want to talk a little bit about the physiology of the heart, at least start talking about the first part of it. In the physiology of the heart, we've got a couple of different aspects to talk about. The heart muscle itself is kind of a weird kind of a tissue as muscle tissue goes. It's not like smooth or skeletal tissue, in that it has to have an innervation each time that it contracts. It's a muscle tissue that literally, in a living condition inside of a living body, can initiate its contractions on its own. And by doing so, the atria will contract somewhere in the neighborhood of about 60 beats per minute when left to its own recourse, and the ventricles about 20 to 40 times. So if we've got 60 on the atria and 40 on the ventricle, we've obviously got a little bit of uncoordinated system that kind of need a little bit of control because we're not synchronized there. Now the heart basically does a nice job typically of beating about 75 on the average, 75 beats per minute, which would give you about 6,000 quarts of blood pumped a day. The heart can go up, go down on a regular basis throughout the day, depending upon the type of exertion that's going on in the body. If we are exercising in a young, healthy person maximally, the heart is an amazing structure, and that it can put out the amount of blood that would be equal to turning on a bath faucet full go. That's how much blood can be put out by the heart in a young, healthy, athletic adult, exercising at maximum heartbeat, like somewhere in the neighborhood of 170, 180 beats a minute, which is as high as it can go in a young adult. Obviously, this couldn't happen in an uncoordinated system like we just talked about. So the nervous system, basically the heart is going to be controlled by 90% of it. It's going to be controlled by the nervous system, specifically the autonomic nervous system. And the autonomic nervous system, as you know, is two branches. It has a sympathetic part and a parasympathetic part. The sympathetic part would be the part that would increase the heart rate, and the parasympathetic part would be the part that would decrease the heart rate. Now, there's another part of that system that's called the intrinsic control system. Intrinsic basically means from within, so it's got an internal system that controls the heart. And that internal system basically sets the rhythm of the heart on its own at about, on the average, 75 beats per minute. Now, every person's going to be a little different, but 75 beats per minute in an average adult would be about correct. So when we want to talk about how this rhythmic system actually occurs, we basically go to the heart muscle itself. The heart muscle basically contracts without nerve impulses in a regular, continuous way. And like I said, it can do this on its own. It's a different kind of tissue. There's special tissues that are involved in the heart also that help to make this intrinsic conduction system work. The first part of it is the sinoatrial node, which is typically called the SA node, up in the right atrium. It's called the pacemaker because it basically initiates each heartbeat, and that's why it's called the pacemaker. So without the SA node initiating the nervous impulse that starts each heart rate, there is going to be no heartbeat overall. The second part is the atrioventricular node. Atrioventricular node would be somewhere down toward the bottom at the junction between the atria and the ventricles. So the sinoatrial node will initiate, it will pass off to the atrioventricular node or the AV node, then it passes off to the atrioventricular bundle. The AV bundle, which is also called the bundle of His, is in the interventricular septum. Interventricular septum is basically that wall between the two ventricles. So this nervous tissue is a bundle of nervous tissue there at the top part of the interventricular septum. The second last part of it is where that interventricular area, AV bundle, separates and branches into the right and to the left atrium, which is what we call the bundle branches. The bundle branches eventually go into each of the walls of the ventricles and branches off into fibers that eventually will innervate all the tissue, all the cardiac tissue of each of the ventricles, the right and the left. And these are called the Purkinje fibers. So they spread the impulse across the ventricular wall muscles. In this diagram, they're going to show you all the different parts of the intrinsic conduction system. Sinoatrial node being right here, atrioventricular node here, the AV bundle right here at the upper portion of the interventricular septum, and then the little fibers that the branches that come off of that, which lead to the right and to the left ventricle, and eventually branch into fibers that take the impulse to the tissue, which are the Purkinje fibers. So initially, the contraction of the heart is going to be initiated by an impulse that comes from the sinoatrial node, the SA node, which is also, as I said before, called the pacemaker. If this sinoatrial node is not working correctly, it throws the whole system off. So obviously this is a very important part of keeping that rhythm. And as usual, there goes my phone. And remember to turn that off. Eventually, the sinoatrial node will initiate the depolarization, and this depolarization is going to move from the top of the heart across to the other atria, then down into the ventricles. So basically it moves in one direction, kind of like the nervous impulse itself. The wave of contraction is going to move from the right atrium, spread to the left atrium, move all the way down into the ventricles. So it goes in one direction. So once the SA node starts the heartbeat, this impulse is going to spread across, spreads to the AV node, and then it will spread across to the other atria, and both of the atria will contract in unison. As the impulse gets down to the bottom of the AV node, the impulse is going to pass through the AV bundle into the bundle branches and into the Purkinje fibers. Eventually, this is going to cause contraction of the ventricles. Now, the ventricles are going to contract basically in an opposite direction from the atria. The ventricles will contract in opposite direction of the ventricles. The ventricles are going to basically squeeze in a motion that pushes the blood, that pushes the contraction from the bottom to the top. In other words, forcing blood from the ventricles upward toward the atria. So blood is ejected from the ventricles into the aorta and the pulmonary trunk from the bottom of the ventricle toward the top, which is where those major vessels are located at the top of the ventricles, pushing blood through the semilunar valves. Now, here once again we take a look at the direction that the impulses move. We start with the sinoatrial. You can see arrows over here to the right atrium, so it's going to spread quickly to the right atrium, and also down, to the left atrium, and quickly down the right atrium. As it goes down to the bottom, it's going to pick up, that impulse is going to be picked up by the atrioventricular node, the AV node, and quickly that impulse will then be shot down the intraventricular septum into the atrioventricular bundle of His. This is one of our common types of heart problems with the intrinsic conduction system, and that sometimes between here and here, between that intraventricular bundle and the bundle branches, we have a block. So whenever there's a block here and the impulse is not getting down through here, we have a lack of ventricular contraction. So we have the atrium contracting, and then the ventricles not doing their job. So that's a big problem. That's called a bundle branch block. So eventually the impulse makes its way onto the branches, the bundle branches, and eventually down into the branches overall that spread the impulse to all parts of the cardiac muscle on the walls of the ventricle. As they contract, they do a ringing motion, and that ringing motion pushes the blood upward toward the atria, and it'll push the blood out of the right ventricle into the pulmonary trunk and out of the left ventricle into the aorta. A couple of things that happen. Typically, people have heard about heart murmurs. Heart murmurs are basically different sounds that you hear, and a lot of times these valves that are opening and closing are going to make very definite sounds. When they're not operating the way that they're supposed to, they'll be allowing, maybe they don't shut quite properly, or when they do shut, they push back into the ventricle or into the atria and have too much laxity and cause a little swishing sound, which would indicate to a doctor that has a trained ear, it would indicate to him that there's a problem with that valve. So whenever there's insufficiency in any of these valves, either the AV valves or the semilunar valves, there will be an abnormal extra sound at the end of each of the heart sounds, the lubbed-up sounds, and he'll know that for some reason there's probably some leakage of blood that's going through that valve because of insufficiency. It's called a heart murmur. I have a particular heart murmur that is called mitral valve prolapse, which is one of the most common of all the heart murmurs. I forget which percentage it is, but it's a pretty high percentage of Americans that have the mitral valve prolapse. And in a mitral valve prolapse, basically what happens is when the left ventricle contracts and pushes against the mitral valve has a little bit of extra stretch to it, and it will, when it closes, the blood pushes it far back into the atrium, and in some cases far enough back to where it actually opens a little bit and leaves some of the blood from the ventricle to seep back into the left atrium. And that's why it's called a mitral valve prolapse. Prolapsing means that it moves back too far, and so there's a little bit of leakage there. A mitral valve prolapse can cause some people to have pain in their heart. It can also be something as benign as having a sixth finger. You basically have it, and you know it doesn't cause you any problems. It's just this is there. So a lot of times people don't even know they have it unless they go through a routine cardiac checkup. I happened to get a cardiac checkup when my father had a heart attack. Me and my brothers all had cardiac examinations, and they found out that 2 of the 4 of us had a mitral valve prolapse, as well as my father. not all that uncommon. Now, when the heart beats, what we said, the heart is going to beat at approximately 75 beats per minute on average, an average adult. Okay. And the maximum heart rate for each person is going to be a little bit different. Okay. But when it does beat, it has parameters that it usually goes through. When physicians are talking about a person's heart rate at rest, a person that will have a rapid heart rate would be one that would be over 100 beats per minute. That would be pretty fast for a normal person. It might indicate that that person is sick and that the body is making some adaptation. It may also mean another of other implications, very high blood pressure maybe, or some other circulatory insufficiencies throughout the body. The opposite of that is also true in a bradycardia situation where a very slow rate, a heart rate, is going to be less than 60 beats. So if it's over 100, it's going to be tachycardic, and if it's under 60, it's going to be bradycardic. Now, bradycardia typically occurs in a normal person at rest if that person is fairly healthy, especially people that exercise on a regular basis. That typically conditions your heart, makes your heart more efficient, and which means that your heart doesn't have to beat as many times to deliver the same amount of blood. A person who exercises in a cardiovascular way 3, 4, or 5 times a week is likely to have a heart rate that's in the 60s or maybe even in the 50s. An old timer like myself who does exercise for 5 or 6 times a week, my heart rate frequently is at 60 or sometimes even below it. Very highly trained athletes sometimes can be extremely low in their resting heart rate. When I went to college with a gentleman who was in extremely good shape. He was on the basketball team that ran a fast break, kind of a very fast-paced offense. And so he ran up and down the floor all the time. He was in great shape, and he had a resting heart rate in the 40s. He was perfectly healthy. So bradycardia can be because of insufficiency somewhere in the body. It can also be because the body's adaptation to training. A couple of other things I wanted to mention. When I talked about the homeostatic imbalance we call the heart block, when we get into talking about the electrocardiogram is going to have some indications on the paper where the heart rate will show a dip in a line, and then it will go straight up into a spiked point, and then it will come back down again, and that is basically when the ventricle contracts, and that's called the QRS complex. Typically, when a doctor is looking at a person who has a bundle branch block like I talked about, the QRS won't go up and down like a triangle. It'll go up about halfway, and it'll go straight across and then down to the S. And so it looks, very different from a normal QRS complex. You'll know what I'm talking about when we get into the electrocardiogram a little bit later. We've already used the term ischemia before. Ischemia basically refers to a lack of adequate blood supply. And when it comes to the heart, this ischemia can cause a great deal of problems. One of the things that can happen in the heart, when the heart has ischemia, it can lead to something called fibrillation, which is a rapid, uncontrolled beat of the heart, which is similar to, and I think I used that term before, a ringing kind of a situation. The book terms it as looks like a bag of wiggling worms. Fibrillation basically is non-functional. The heart is wriggling, around and it's not pumping any blood, and eventually can lead to death. Many times when a person goes into fibrillation, they typically follow up with a cardiac arrest, which means the heart stops. And when the heart stops, then we have to defibrillate. And basically what defibrillation does is it literally stops the heartbeat and it makes it start over again. And a lot of times when the defibrillators are used, the person gets shocked and their heart temporarily stops, and then hopefully when the SA node picks up again, when the pacemaker picks up the beat again, it will start it in a normal rate again. So those are a couple of homeostatic imbalances that are connected to what we were talking about there. The cardiac cycle is the last thing I want to talk about here. The cardiac cycle basically is going to talk about what's happening in the heart at each point. Okay, in the cardiac cycle, we're going to have the atrium contract. Then the atria will relax as the ventricles are contracting. When we have contraction or relaxation of the heart, we generally term this as contraction or relaxation of the ventricle. We're not really referring to the atria because the ejecting or discharge chambers of the heart are going to be the ventricles. So we're basically talking in terms of heart contraction or heart relaxation. We're talking about, in general, we're talking about the ventricles. So when the heart is in contraction or ventricular contraction, we say that the heart is in systole, and when it is relaxing, we say it's in dystole. Systole and dystole. So there are three basic parts of the cardiac cycle: mid to late diastole, ventricular systole, which is when the two ventricles are contracting, and then early diastole. As you can see, in mid to late diastole, when the ventricles are relaxing, there's a starting of draining of blood that initially starts to go down. As we said, gravity basically pulls blood down into the ventricle. In the late part of diastole, then the atria will contract and forcefully push the rest of that additional blood down into the ventricle. In ventricular systole, the ventricles then contract and they eject their blood out through the major arteries. The right side, the right ventricle, pushing its blood through the pulmonary trunk, and the left side pushing its blood through the aorta. In the last part, we have the early diastole. That's when blood is filling up the atrium again, and there's always just a little bit of blood left over from each contraction in the ventricle. It doesn't completely empty, so that's why it has a little bit of blood left at the bottom here. Then we'd go back to mid to late diastole, where the blood starts draining back down into the ventricles again. So, to recap the cardiac cycle, the events that are happening, mid to late diastole is when the blood flows from the atria into the ventricles. In ventricular systole, we have contraction of the ejection chambers, which are the ventricles, which pushes blood out through the main arteries. And then in early diastole, the ventricles are going to relax again, and the atria are going to start to refill. So there are three major parts to the cardiac cycle. Whenever the heart's beating, we're going to hear two sounds. We're going to hear a lub-dup sound, is the way it's been described. The lub-dup sounds, or the heart sounds, are the result of the contraction of the ventricle and the subsequent relaxation of the ventricle. When the ventricles are contracting, that's the lub sound, which is produced when the ventricles contract and push blood up against the AV valves, and they slap shut. This is a little bit louder sound, and it's a little bit longer sound. So it's lub-dup, lub-dup. And the second sound, the dup sound, is when the ventricles have finished contracting and go into relaxation, and the blood that has been forcefully pushed into the major arteries leaving the heart is trying to push back into the ventricles and causes the semilunar valves to slap shut. So the second sound you hear is the semilunar valve slapping shut. So the lub sound, AV valves, dup sound is the semilunar valves. And that's the cardiac cycle. We will pick up the next time we talk. We will, I think I'm going to send you a little YouTube video on how to read electrocardiograms, EKG. ECG is what it's also called. EKG and ECG, also all the same thing. Has a bunch of parts to it. They're going to describe what you'd be looking at as you look at each part of the cycle and be able to interpret it. And then we'll get into talking about some of the other aspects of how the heart works. So that's it for today. Adios, amoebas.